Buongiorno, signore e signori. I am quite happy today because we will be taking a look at Girolamo Cardano's derivation of the formula to solve the depressed cubic. Cardano is a 16th century Italian mathematician. He would have lived in Italy's Renaissance period, and he published this derivation in his 1545 Latin language book on algebra, Ars Magna. This in Latin is translated as great art. I will keep this brief, and will probably get some details wrong, but during this period, many Italian mathematicians dueled for monetary and or publication right purposes on who would be able to solve certain cubic equations. Yes, that was a thing. It's kind of an exotic form of gambling, so to speak. There is some drama in particular between Cardano and another mathematician named Tartaglia, which you can look up about. I'm certain that they have a teacher-student relationship, actually, though who is the teacher and who's the student, I cannot technically remember. Now, this construction of Cardano's proof is accredited solely to William Dunham from his text, Journey Through Genius. So this is obviously a secondary source. Text of his proof. And this is the front page of my copy. I'm quite proud to have this book. So first, let me mention what a depressed cubic is. A depressed cubic is essentially a cubic without a quadratic term. See, here you have a monic x cubed with no coefficient in front of it, except 1. You have a linear term with a coefficient m in front of it, and then you have on the right-hand side of the equation a constant term m, where n and m are real numbers. It turns out that solving this family of cubics is easier than solving the general cubic equation, which is just this guy. ax cubed plus bx squared plus cx plus d equals 0. And once again, a, b, c, and d are real numbers. Yeah, solving this guy is much, much easier. And I will later go on to show how we can use Cardano's depressed cubic formula to understand a very tedious, definitely tedious, and perhaps convoluted way of solving the general cubic equation. But that will be much later in the video, or save for part 2. So let me go about the introduction of how Cardano sets up his proof. Imagine you have a cube, let me get my ruler, of dimensions t by t. So this is length t, this is a length t, and this is a length t as well. We're going to make an arbitrary cut of length u over here. So here's a one-dimensional way to take a look at it. So the remainder length over here will be t minus u. As you can see in my three-dimensional drawing, I have one cube here, and its dimensions are of dimensions t minus u, and t minus u. The blue cube, alternatively, much easier, is just of dimensions u, and u. So, knowing this, we're going to go and subdivide this cube into 6 different regions, 6 different solids of each having their own volume, which is why I've written down V1, V2, V3, V4, V5, and V6. These are the corresponding volumes partitioned inside this solid. One thing to keep in mind, since t represents a geometric length, and that u is a small cut inside it, that t must be greater than u. We must keep that in mind, and therefore that t minus u has to be positive. This is important for Cardano's. So I hope you understand the framework now, and I will go on to show Cardano's depressed cubic formula derivation. I'll see you in the next footage. Hi friends, hope you're doing well today. So now I will like to dive straight into Cardano's derivation of the depressed cubic formula. I would like to make a brief apology for an error I made in the previous introductory video. The small blue cube that I drew inside the largest cube, that actually has dimensions t minus 2 on all sides, so a volume t minus u cubed. And similarly for the smallest black cube, side length u and volume of u cubed on all sides. Okay, with that being said, Remember what a depressed cubic is, and that we make, yeah, that's a depressed cubic, and that we're making a small line segment cut U in our original line segment T, and we are going to break up our giant cube of volume T cubed into 6 smaller prisms, then add them up. As you can see here on the screen, I've already done so for you. These are the corresponding volume formulas. So the sum of all these volumes will equal T cubed. So I end up with this equation over here. Here is where we start using the algebra now. Oh, and in case it does not seem obvious where these volume formulas come from, I will be making a, wait for it, yay, an arts and crafts video on assembling these cubes together through, prisms together through paper cutting. I personally think we need to incorporate more play into math education, and I'd like to give a big shout out to someone who successfully does this on YouTube, math musician Vi Hart, with some ways you can discover math by doodling while procrastinating in math class. So please follow her channel if you can, as seen on my play card here or in my video description. Okay, anyhow, back on track. So our volume equation should look like this, and we will now move this first volume segment, this u cubed term, onto the left-hand side. So we end up with a difference of 2 cubes expression, t cubed minus u cubed. Now, with one factoring trick, we are going to end up with an equation that is of similar form to the depressed cubic that we have, except it's all in terms of t minus u. So first, what you're going to do is see these 3 terms over here. We're going to factor out a t minus u from them. We end up with this. And then we can simply simplify the terms inside here. U times t gives you ut to u, whatever, multiplication is commutative, and then u times minus u is minus u squared. So the u squareds cancel out with each other, and all you're left with is free tu. So this t cubed minus u cubed and this free tu, given your substitution of x equals t minus u, these guys correspond to the m and n parameters of our depressed cubic. N, which is the constant term, is t cubed minus u cubed over here. M, which is the linear coefficient, is free tu. Now, these 2 parameterizations are going to save us. T and u are variables, whereas m and n are constants. So we are going to solve for both t and u in terms of m and n through a series of substitutions. So this is what we're going to do. We have n over here, and we have m. For this expression, make u the subject, so you end up with m divided by free t. I'm going to plug this expression back into this original equation up here. Now I end up with this mess, and now I go and multiply both sides by 27t cubed. And just using your fancy elementary algebra, you end up with this sextic polynomial. Which kind of, I know, doesn't look nice, but because 6 equals 2 times 3, and we can expand it out like this, we can make another clever substitution that z equals t cubed. And so this expression simply becomes a quadratic. And what do you do when you have a quadratic? Well, you can use the you love it or you hate it quadratic formula, and then solve for what z should be. Now, Dunham, they go about this differently. When they solve their quadratic equation, they've made the quadratic a monic, so they divided 27 by both sides. But I'm not going to do that. I'm just going to do it my way. So just to quickly recall, this is the quadratic formula. And if you know how to use it correctly and plug it in, you should end up with this. Now, just to make looking at the algebra a bit nicer, I'm going to express 27 and 4 in terms of their prime factorizations, so 3 cubed and 2 squared respectively. Now we end up with these nasty terms we have to go and simplify. And then if you go and split up this one single fraction by the plus or minus sign into 2 fractions, we end up with n over 2 plus or minus 1 over 2 times 3 squared times square root of 3 to the 4 n squared plus 2 squared times 3 m cubed. Now, I'm going to make a somewhat counterintuitive move here. it doesn't seem to help at first, but it actually does. That 1 over 2 times 3 squared fraction over here, express it in radical form, square root radical form, which would be this. If we do that, we can recombine it into this original radical we have, and now the magic happens, which is essentially cancellation. You break up your single fraction in the radical as two fractions once again, just like I did with the plus or minus here. And you end up with that, oh, hey, you have a 3 to the 4 at the top, 3 to the 4 to the bottom here, 2 squared to the top, 2 squared to the bottom. These guys cancel out. And I simply end up with this expression, n squared over 2 squared, and m cubed over 3 cubed, which can simply be root factored out as n halves squared and n cubed squared. Now we can make a back substitution on z, because remember, this is solved in terms of z, not t. So recall that z equals t cubed. We end up with t cubed equals this guy. Now take the cube root of both sides of the equation. We don't have to worry about plus or minus problems here because cubic functions are odd. And we're done. We found a multivariable, two-variable function for t expressed in terms of m and n. Now we can back solve for u just simply by using one of these relations again. So I'm going to do it in this manner. So I end up with this. So u, the multivariable function u, is almost the same as t, except instead of a positive n over 2 to the left of the plus or minus sign, you have a negative n over 2. In my opinion, it is very beautiful that we have the linear coefficient term being divided by 3, the degree of the cubic, while the constant term is divided by 2, and each fraction is raised to the power of its denominator, respectively. Similarly, both parameterizations of u and t look identical, except for the fact, well, that I stay between u and t about the sign. And if you were to interpret geometrically, you could think of, at least for inside the cubic radical, the difference between u and t is that u is being horizontally translated, however you describe that in 3 dimensions, to the left of origin by a distance of n over 2, whereas t is horizontally translated to the right by a distance of n over 2. And this seems to me to intuit or indicate that the solution has a kind of translational, a translational or perhaps vertical reflectional symmetry. I will admit, though, that the nested radicals are a bit cumbersome, though, in my aesthetic taste. But we are not done yet because the solution we want is x equals t minus u. So all we have to do is take these two nasty expressions with this one first and this one second and subtract them from one another. And lo and behold, you have ended up with your solution. It is in the form of two terms being subtracted by another where you have nested quadratic and cubic radicals. I'm going to do something nice and extra here now, given our solution is a two-variable function. By the fact that it's a two-variable function, we can graph a 3D surface of it. Hopefully from visualization, we can see the symmetry. Last time I made 3D plots was for my Calc 3 course, actually in 2014. So let's see whether I'm still a noob or scrub, as the Gen Z people say. Briefly, I would like to thank Monro Education Community College for providing their Calc Plot 3D applet to the public domain that I happen to use. For this particular topic, I think it's best if we take a look at the small two-variable functions of u and t first before we combine them together for x of m and n. I have my 3D graphs from the site bounded between -2 and 2 for each of the axes. And in terms of the way I have my drawings screenshotted here, the positive x-axis will be jutting out to the left. The positive y-axis will be jutting outside of the screen towards me. And the positive z-axis will be moving vertically up top. So now let me scroll through what all of these 4 graphs look like. You there? Okay. As you can note, especially from the U of m and n and t of m of n plots, where you make the sign negative, you have a negative sign over here. You seem to have a very spiral staircase-like plot, forming a cubic curve or trace. I think the best way one you can see it in is this guy example. A bit hard to see, but follow the green and then go to the orange. And we always seem to have a dip in the surface in one of the four octants that contains the negative z-axis. So there's your pretty pictures. I will be plotting the four solution surfaces of x of n where m, our actual solution curve, on live on the website. Please wait as I transition to the website now. So here it is, ladies and gentlemen. This is what the 3D graph of the depressed cubic looks like on live. So you can see that once again, there's a bit of like a cubic trace. You might say there's actually two different cubic traces, one along the yellow side over here, can't really draw it out, and another along the orange, more sided region over here. And you kind of end up with, I would like to say like a wine glass kind of like shape if you connect like these two ends of the white rims together, which is not part of the graph curve. And I'll just give you a quick look of it by rotating it around. So this is the case where I have a positive sign and a positive sign from when we made the parameterization and we used the quadratic formula. And now here's one where I believe this is I make the first expression in the t function positive, and I make the u function negative. So this is what it looks like. So comparing them, yes, I'm starting to see it now. So for at least this example, the dip begins to really happen where you have the wine glass shape along the y-axis, whereas this one, the dip sort of happens along the, there we go, along the negative z-axis. So here a dip happens along the positive y-axis. Here you have a dip along the negative z-axis. You could call it such a shape like a wine glass or something like that. And here, if we take a look at this particular example, here the sign is, no, sorry, this one, the sign of the t function is negative and the sign of the u function is positive. So we were to go and compare this guy. Seems as if, yeah, you can sort of see that like it's been like flipped around about the xy plane, sort of like have a reflection. I can imagine if I were to somehow get this into like a 3D simulator, it would kind of like oscillate about, kind of like a wave, kind of like the patterns you get in, what do you call it? Vibrations of a drum. As like the membrane like vibrates back and forth. That's kind of like the picture you would get. And then finally, here's one where all the signs are negative. As you can see here, you have a much more nicer looking wine glass shaped sign over here. So when both signs are positive, you can clearly see this really nice wine glass shaped looking thing. And when they're not, when you're alternating the signs, you kind of end up with this big giant dip thing over here. The wine glass kind of looks like it's edged at a very daunting curve. And yeah, finally, I graphed the trivial case of just like the exact same function. I basically make t of mn and u of mn the same. So I'm basically subtracting the same function by itself. And I initially thought that I would be getting just the xy plane, therefore no solutions for, or rather all the solutions for z, all the outputs are 0. But surprisingly, I do get it, but I have a portion of the xy plane missing here, kind of traced away by this curve, if you will. I guess like by the two square roots. And I have a feeling it's because the square root can only take in positive and negative arguments of a sort. That explains why we have this missing shape in here. So yeah, that's essentially it for my depressed cubic video extravaganza. In the next video, in this installment, I will take a look at how you can use the depressed cubic, surprisingly, to go and find the general solution of a cubic. I mean, in other words, find the general solution of this guy, y of x equals ax cubed plus bx squared plus cx plus d. I hope you enjoyed the series, and please stay tuned for the next installment. Until then, everyone, ciao.